discussed random variables and how to characterize them with the help of CDF, PDF, PMF, etc. The CDF, PDF and PMF, they are complete representation of a random variable. Now we will see how we can represent a random variable partially. We can characterize a random variable partially by moments. So we will start with the definition of expected value of a random variable. The expected value of a random variable x is defined by these two relationship. If x is continuous, then this is the integration of x into fx of x, PDF. And similarly, if x is discrete, it is the summation of the product of x into px of x, and the limit of integration or the summation we have to properly define. When we define expectation, we want that this value is unique. So, for that one condition is imposed, that is x mod of x fx of x, that is absolutely. We want mod of x into fx of x should be integrable over the limit minus infinity to infinity, or in the case of discrete, mod of x into px of x should be summable for the range of the random variable x. So, we have defined the expected value or average value. This is the average value of the single random variable x by this relationship. Now, we will define the expected value of a function of a random variable. Suppose y is equal to gx is a real valued function of a random variable x. Then e of gx, this is given by, again it is integration from minus infinity to plus infinity gx into fx of x dx. So, in the case of continuous x. Now, if I consider discrete x, then it will be summation over x of gx into px of x. So, that way we can find out the expected value of any function, any real valued function of gx. Of course, we have to be careful that this expected value is also unique, and for this we require these two conditions. So, we have defined the expected value of a function of a random variable. Particularly, we will discuss moments. So, moments, first of all we will define moment for a positive integer n, nth order moment is defined as e of x to the power n, that is the nth order moment. This is given by integration from minus infinity to plus infinity x to the power n fx of x dx. This is the nth order moment. Similarly, nth order central moment we can define. We have to consider the deviation of x from the mean x minus mu x, that is. So, e of x minus mu x to the power n we have to consider, that is called nth order central moment, and it is given by from that is integration from minus infinity to plus infinity x minus mu x to the power n fx of x dx. So, that way we define the nth order central moment. Particularly, we are more interested with e of x square, that is when n is equal to 2, that is the mean square value of a random variable. Similarly, variance, that is sigma x square. So, it is a measure of variability of the random variable. So, it is given by x e of x minus mu x whole square, and this we can also write in terms of that is mean square value e of x square, mean square value minus square of the mean. This expression we can simplify. So, that way we can define mean and variance, which are two important parameters of any random variable x. So, we have defined moment, and we will define now moment generating function mx of x as the name implies, it is used to generate the moments. So, moment generating function is a function of a variable s. Okay. So, the s is usually a real number. So, this is defined as e of e to the power s x, that is expected value of e to the power s x, and that is equal to integration from minus infinity to infinity e to the power s x f x of x dx. So, this is the moment generating function. So, it is defined over this minus infinity to infinity, that is the range of the random variable x. So, that way we assume that this random variable x is defined over the range R x, which is the real line from minus infinity to plus infinity. So, that way we have defined the moment generating function. So, it is essentially a function of single parameter s, and mx can be used to generate the moments by the relation. We will see how we can have the relationship, and that is e of x to the power n is equal to nth derivative so nth derivative of mx of s at point s is equal to 0. So, this is the relationship. We can find out the nth order moment from the moment generating function by taking the nth order derivative at s is equal to 0. How we can get this relationship? Let us see e of x. How we can find out this relationship? Let us examine. We will start with suppose ddx of dds of mx of s. Okay. If we see this, what it will be? It is the dds of that integration from minus infinity e to the power s x f x of x dx. Okay. Now, this is a differentiation with respect to s. We can take differentiation inside, and we will get minus infinity to infinity. So, since it is a function of x and s, we will take the partial derivative del s of e to the power s x f x of x dx. Okay. So, this we will get as minus infinity to infinity. Now, this will be if I take the partial derivative with respect to s, we will get x into e to the power s x f x of x dx. Okay. So, therefore, if I put ds of mx of s at s is equal to 0, what we will get? This one will become 1. So, we will get that is equal to minus infinity to infinity x f x of x dx, which is nothing but e of x. Continue in a similar manner, we can arrive at this relationship that e of x to the power n is the nth derivative of mx of s with respect to s, of course, and nth derivative with respect to s of mx of s at point s is equal to 0. S is equal to 0. So, that way this is the utility of the moment generating function from so it encapsulates all the moments. So, therefore, from the moment generating function we can generate all the moments. We can consider one example. X is suppose standard normal variable, standard normal random variable or standard Gaussian. X, this is the notation, x is normal 0 1. What does it mean? It is the normal distribution with mean 0 and variance 1. So, that means in this case f x of x, this is the PDF that will be equal to 1 by root over 2 pi e to the power minus s square by 2. This is the PDF. We have to find out mx of s, and that is equal to e of e to the power sx. So, if I put the expression for the expected value, we will get this as integration from minus infinity to infinity e of e to the power sx. We will derive the moment generating function, this standard normal random variable. So, mx of s by definition it is e of e to the power sx. So, it is given by integration from minus infinity to infinity e to the power sx, then PDF is 1 by root over 2 pi into e to the power minus x square by 2 dx. So, this we can simplify like this. So, plus this same exponential. So, it will be plus sx. Now, this we can write further as 1 by root over 2 pi e to the power, if I take half common, minus half common, then s square minus 2 sx. So, now we can complete this to be a perfect square. If we add s square here, then we have to subtract. So, because of that we will have another term half of s square into dx. Okay. So, this is the expression. Now, let us see, we can take e to the power half s square common. So, e to the power s square by 2, then integration minus infinity to infinity 1 by root over 2 pi e to the power minus half of s. So, what we will have? X minus s whole square dx. Now, we observe that this is a Gaussian, this is a Gaussian with mean s and of course, variance 1. So, if I integrate this Gaussian from minus infinity to plus infinity, this integral will be equal to 1. So, this integral will be 1. Therefore, mx of s is equal to e to the power s square by 2. So, moment generating function for the standard Gaussian is e to the power s square by 2. So, now we can use this moment generating function. For example, if I take the first derivative, e of x will be equal to first derivative, that is mx dash of s at s is equal to 0. Okay. So, this we will get as, so this will be equal to 0. Similarly, e of x square is equal to mx double dash at s is equal to 0, and this will be equal to again 1. So, that way we can find out all the moments of this random variable, namely the standard Gaussian. So, that way we see the utility of the moment generating function, and we will be using the moment generating function in our subsequent proofs. So, we define the moment for a single random variable, we can define the moments for multiple random variable. So, for two random variable x and y, the joint moment m plus nth order moment. So, joint moment of order m plus n. So, this is defined as e of x to the power m y to the power n, that is equal to, again it will be double integral, then you are multiplying x to the power m and y to the power n with the joint PDF f x y at point x y, and you integrate with respect to dx and dy. So, this is the expression for joint moment of order m plus n. So, now if I take m is equal to 1, n is equal to 1, we have the second order moment, which is also called correlation between x and y, and is given by e of x y is equal to, now here m is 1, n is y 1, therefore, it is x y into joint PDF into dx into dy integration from minus infinity to plus infinity. So, that way we can define the joint expectation or second order moment of the random variables x and y. We can define the covariance of the random variable x and y. So, the covariance between x and y is given by this curve of x y, that is equal to e of x minus mu x into y minus mu y. So, we consider the deviation from the, each random variable x minus mu x, and similarly deviation from mu y, y minus mu y, and this quantity is known as the covariance. And we can also define the correlation coefficient rho x y, that is equal to covariance of x y divided by sigma x into sigma y, where sigma x is the standard deviation of x, which is the square root of variance, sigma y is the standard deviation of y. This coefficient rho, which usually lies between minus 1 and plus 1. So, therefore, the correlation coefficient rho x y is defined as covariance of x y divided by sigma x into sigma y, where sigma x is the standard deviation of x, which is the square root of the variance of x. Similarly, sigma y is the standard deviation of y. Now, this correlation coefficient is an important parameter to characterize these two random variables x and y, and we can show that rho x y lies between minus 1 and plus 1. Now, once we define the covariance or correlation coefficient, we can define uncorrelated random variable. Uncorrelated random variable x and y are uncorrelated if covariance of x y is equal to 0 or rho x y is equal to 0. Correlation coefficient is 0, implies that E of x y is equal to mu x into mu y. This is the relationship for x and y to be uncorrelated. Similarly, so x and y are uncorrelated if covariance of x y is equal to 0. Equivalently, E of x y is equal to mu x into mu y. Otherwise, x and y are called correlated. So, what is correlated random variable? So, covariance is not equal to 0. We will discuss this concept of correlated random variable, but we want to establish one relationship. We know when x and y are independent. Suppose if x and y are independent, y are independent, then they are uncorrelated. But the converse is not generally true. So, independent random variables are always uncorrelated, but uncorrelated random variables need not be independent. We can consider this result. We know what is x and y are independent. X and y are independent. implies that joint density f x y at point x y is equal to f x of x into f y of y. Joint density is product of marginal density. Therefore, this is the definition of independence, and this is for all values of x and y. So, therefore, we can find out E of x y for two independent random variable x and y. E of x y will be equal to integration, double integration from minus infinity to infinity x y into f x y at point x y dy dx. Okay. Now, we can write this joint density as the product of marginal density, and then this x is there, y is there. So, we can write this integral as the product of two integral, that is integration from x from minus infinity to infinity of x into f x of x dx into integration from minus infinity to infinity y into f y of y dy. So, this is E of x and this is E of y, therefore, E x into E y. Therefore, in the case of independent random variable, E of x y will be always equal to E x into E y, implies that x and y are uncorrelated. So, therefore, if x and y are independent, they will be always uncorrelated. Converse is not generally true. So, what does correlation implies? Correlation is a type of dependence. What type of dependence? If we can show that if x and y are correlated, suppose this is x, this is y. Now, we can approximate y in terms of x by a line. So, correlation means that if x and y are correlated, we can have an approximate straight line relationship between x and y. So, these are the points. Suppose for a particular value of x and y, these are the values of x and y in xy plane, and this can be approximated by this line. So, this is an example of positively correlated random variable. Similarly, and this slope will be determined by the correlation coefficient. Similarly, if the correlation coefficient is negative, this is a this is a negatively correlated random variable. As x increases, y decreases, and here also we can approximate the relationship between x and y by a straight line. But when x and y are uncorrelated, we cannot have a straight line relationship between x and y. That is the meaning of uncorrelatedness. So, that way correlation is a measure of linear relationship between two random variables x and y. Now, if x and y are uncorrelated, we cannot approximate one by the other by plotting a straight line, approximate straight line between them. So, that way correlatedness is a special case of dependence. So, that dependence is linear dependence, that x and y have linear dependence between them, that can be represented by the correlation or correlation coefficient. We will give one example of two-dimensional random variable. This is the notation x y. It is distributed as normal mu1, mu2, sigma 1 square, this is sigma 1 square, sigma 2 square and rho. So, there are 5 parameters and the expression for the joint PDF is this. So, we see that these parameters, this is the mean of these two random variable x, mu2 is the mean of the random variable y, and then sigma 1 square is the variance of x, sigma 2 square is the variance of y, and rho is the correlation coefficient, how x and y are correlated. So, this is the two dimensional Gaussian, and we see that here these 5 parameters are controlling the characteristics of this two dimensional Gaussian. And we also observe that we can show that if suppose x and y are jointly Gaussian, then x will be individually Gaussian. So, what will be f x of x? F x of x in this case, it will be individually Gaussian 1 by root over 2 pi into sigma 1 into e to the power minus half of x minus mu 1 whole square. So, this is the marginal PDF of x. Similarly, marginal PDF of y will be also Gaussian with mean mu 2 and variance sigma 2. So, that way if x and y are jointly Gaussian, then x will be Gaussian and y will be Gaussian. But if converse is not again true, if x is Gaussian, y is Gaussian, x and y need not be jointly Gaussian. Now, we see that this correlation coefficient, which is a measure of correlation between x and y, and we see what happens if rho is equal to 0. If rho is equal to 0, that means x and y are uncorrelated. X and y are uncorrelated. So, in that case, what will happen, that f x y at point x y is equal to, now this rho will be equal to 0. So, everywhere if we put rho is equal to 0, then we will get 1 by 2 pi sigma 1 sigma 2 into e to the power minus half of x minus mu 1 by sigma 1 whole square plus x minus y minus mu 2 divided by sigma 2 whole square. Okay. So, this now we can write as 1 by root 2 pi sigma 1 into e to the power minus half of x minus mu 1 by sigma 1 whole square into 1 by root 2 pi sigma 2 into e to the power minus half of y minus mu 2 whole square. Okay. And this is equal to, that is marginal density of x into marginal density of y. So, what we observed that if x and y are uncorrelated and jointly Gaussian, then x and y will be independent also. Therefore, what is our conclusion? If x and y are uncorrelated and jointly Gaussian, then x and y are independent also. Usually, uncorrelatedness does not imply independence, but in the case of jointly Gaussian random variables x and y, that uncorrelatedness imply independence. So, for the case of Gaussian, jointly Gaussian random variables x and y, uncorrelatedness uncorrelatedness implies independence. Okay. So, this relationship uncorrelated generally does not imply independence, but in the case of jointly Gaussian random variable, uncorrelatedness imply independence. So, that way we define the moments of the random variable, particularly joint moment or second order moments, covariance, correlation coefficient. Also, we discussed about the jointly Gaussian random variables, how it is characterized by 5 parameters, and what happens when the correlation coefficient is equal to 0. Next, we will discuss about conditional expectation. We know the definition of conditional PDF and PMF. Suppose x and y are continuous random variable. If x and y are continuous, then the conditional PDF of y given x is equal to x. So, given x is equal to x, the PDF of y is given by this, that is joint PDF divided by marginal PDF. Of course, we require that f x of x need not be equal to 0, f x of x not equal to 0. Similarly, if x and y are discrete random variables, then the conditional probability mass function of y given x is equal to x is given by this. This is the conditional PMF at point y given that x is equal to small x, that is equal to joint PMF divided by marginal PMF. Here also we require that Px of x is not equal to 0. So, once we have the conditional PDF of the random variable y given that x is equal to small x, similarly conditional PMF of y given x is equal to small x, then we can define the conditional expectation of y given that x is equal to x, E of y given that x is equal to x. So, this is for the jointly continuous random variable x and y, it is given by this integral relationship, and for the discrete random variable x and y, this is given by the this sum relationship. So, that way we have defined the conditional expectation of y given x is equal to x. We observe that this conditional expectation, suppose for a given x, what is the conditional expectation or average value of y? If we fix x, then what are the likely value of y and what are the likely values of y and what is the average of y? That is the conditional expectation given that we have an observation x is equal to small x. This is a very important parameter, and this is, suppose if I have x, what is the expected value of y? So, we can plot, suppose x versus E of y given x is equal to small x. So, we can get some curve which is known as the regression. Regression of y on x, and this parameter is also, suppose if we have to predict y from x, this is the best prediction that x is given, then what is the best prediction under the mean square sense. Suppose you want to minimize the mean square error, then the solution will give us that the resulting relationship is E of y given x is equal to x. So, that is the best prediction of y given that x is equal to small x. We also observe that E of y given x is equal to x, this is a function of x. function of x. So, now if I consider x to be variable, because this is for a particular x, and if we consider x to be variable, then we want this conditional expectation E of y given x, because x will be taking different values, and this quantity is a random variable, of course. This is a random variable, and this can be used to, for example, to find out the expected value of y. So, that way this is a random variable, and its distribution will be with respect to, suppose if x is fixed, then it will be a PDF with respect to y. So, E of y given x is a random variable and a function of x. A random variable, it is a random variable and a function of x, random variable x. Therefore, we can take the expected value of this quantity with respect to x. E of x, Ex of E of y given x. So, when we take the expected value here, it is a random variable is y given x is equal to suppose small x, then we can take the expected value with respect to y. Now, we will take the expected value with respect to x. This will be equal to E of y. So, this is one important relationship. So, that way we will using the concept, we will be using the concept of conditional expectation. Conditional expectation, it is a measure of best linear prediction given that x is equal to small x. So, we discussed about conditional expectation E of y given that x is equal to small x, and also we discussed that considering x to be variable, it is a function of x, and from this expected value, if we take the expectation again with respect to x, we will find E of y. And also the plot of E of y given x is equal to x versus x. So, that is the regression of y on x, and this value, suppose for a given x, what is the best prediction under some sense, under the minimum mean square error sense, that is given by the regression curve. So, that way this condition, just like conditional PDF and PMF, the conditional expectation is also important quantity, and that we will be using in our subsequent studies. Let us summarize the lecture. First, we define expectation for a function gx. E of gx is defined by this integration. So, basically gx into fx of x integration from minus infinity to infinity, provided of course this gx fx should be absolutely integrable. Then we define the different moments. For example, mean mu is equal to E of x, mean square E of x square, variance sigma square is equal to E of x minus mu square, and generally mth order moment E of x to the power m, mth order central moment E of x minus mu to the power m. So, these moments partially describe the random variable. Unlike CDF, which completely describe the random variable, the moments partially describe the random variable. Next, we discussed about moment generating function. The MGF is given by mx of s, that is the expected value of e to the power sx. And the utility of the moment generating function is that we can find out the moments from the MGF. So, that way E of x to the power m is related to MGF by this relationship, that is E of x to the power m is the mth derivative of mx of s at point s is equal to 0. We also talked about joint expectation. Suppose joint expectation of x and y, E of x y, and that is the integration from minus infinity to infinity, from minus infinity to infinity x y into joint PDF dy dx. So, this is the integration, double integration of the product of x y and joint PDF. So, this E of x y is an important quantity. So, it partially describes the random variables x and y. We also define the covariance of x y. It is given by the expected value of x minus mu x into y minus mu y. And we discussed about the importance of covariance, how it expresses the linear relationship between two random variables x and y. Also, x and y are called uncorrelated if covariance of x y is equal to 0, and that also equivalently we can say that if E of x y is equal to E x into E y. We define jointly Gaussian random variables x and y. The joint Gaussian random variables x and y have the joint PDF given by this. So, it is determined by, it is an exponential quantity and it is determined by 5 parameters, namely mu 1, that is the mean of x, mu 2, that is the mean of y, then sigma 1 variance of x, sigma 2 variance of y, and rho is the correlation coefficient. That also we define that correlation coefficient is the covariance normalized by sigma x into sigma y. Thank you.